Transformers power today's AI breakthroughs. But have you ever wondered why every transformer has this normalization layer? What makes it so critical? Let's see what happens if we remove the normalization layer. In attention layers, we compute the query, key, and value vectors by applying linear projections on the input embedding vectors. In the mixture of experts layers, each active expert computes its output using a two-layer MLP. All these computations involve matrix multiplications. To see why normalization is necessary, let's focus on a single output dimension from the linear transformation. Let's denote the input values as x1, x2, x3, and x4, and the output value as z. To compute the output value z, we take the input and multiply it by a learnable weight w. Then we sum them all up. During training, backpropagation calculates gradients. How much the loss changes when we tweak each weight. Here is how it works. Suppose we know how much z affects the loss. By the chain rule from calculus, the gradient at each step is the product of what came before and the local derivative. Think of it like a message traveling down a chain. Each person passes it on, adjusting it slightly based on their local operation. Here, the local derivative of the addition operation is simply 1. We are now ready to compute how much each weight affects the loss, that is, the gradient of the loss with respect to individual weights W1, W2, and so on. Since the operation here is multiplication, the local derivative with respect to each weight turns out to be the input value x sub I. This isn't an issue when the input values are all in a similar range. But what happens when some inputs are much bigger than others? In that case, their corresponding weights receive much larger gradients. This imbalance causes a few weights to dominate the optimization process, making learning unstable. As layers stack up, this problem compounds. Certain activations can explode or vanish, making it very difficult for the model to train and generalize. This is exactly where normalization steps in, ensuring stable, balanced gradients and enabling the network to learn reliably. But what does the normalization layer actually achieve? Given a feature activation x, we normalize the vector by subtracting the average and dividing by the standard deviation. Depending on which group of values we use to compute the mean and variance, we get different types of normalization layers, including batch norm, layer norm, instance norm, and group norm. Here, the h and w are the spatial dimensions, n is the batch dimension, and c is the feature dimension. In transformer models, layer normalization is typically used to normalize the hidden state of each token. Let's build some intuition with a simple visualization. Here we have a single point in 3D space with coordinates x1, x2, and x3. We use this to represent a three-dimensional embedding vector for a particular token. Since a sequence has many tokens, we visualize multiple vectors as a cloud of points. Layer normalization starts by subtracting each vector's mean from itself. All the centered points now lie flat on a single plane. Next, we rescale each vector by dividing by the standard deviation. To prevent numerical issues such as division by near zero values, we add a tiny constant epsilon to the denominator. But just normalizing isn't quite enough. The model needs more flexibility. This is where the learnable parameters, beta and gamma, come in. For example, adjusting the beta value enables the normalization layer to shift the output vectors, thereby giving the model greater flexibility where needed. Similarly, the gamma parameter controls the scaling of the normalized output for each dimension, allowing the network to adjust how much to stretch or shrink each dimension. In recent models, root mean square normalization, or RMS norm, has become increasingly common. It simplifies layer normalization computation by skipping the mean subtraction step. RMS-norm rescales the vectors to a unit sphere. Let's now visualize the effects of the normalization layer. Imagine each token embedding is a 6-dimensional vector. To compute the layer normalization, we first need to compute the statistics, the mean and standard deviation across all 6 dimensions. We can then normalize each dimension by subtracting the mean and dividing by the standard deviation. Because the relationship between the input x and output y in this case is purely linear, just shifting and scaling, if we plot y versus x on a 2D graph, we see a perfect straight line. Here are some more examples. But here's where it gets interesting. When the input has more spread, the output slope flattens out. This effect becomes especially clear when the input vector includes extreme outlier values. When the input vector has high variance, normalization compresses the output values, ensuring they remain within a stable, bounded range. Here are the input-output relationships across multiple layers. While the input-output mapping for each token is linear, the aggregate effect across tokens yields a non-linear S-shaped relationship. We observe a similar S-shaped input-output relationship across multiple tasks and in multiple layers. So here's the key question. If we just want an S-shaped curve, why not use an S-shaped function directly without relying on mean and variance normalization? One classic S-shaped function is the hyperbolic tangent, or Tanh. It's a commonly used activation function in neural networks that maps inputs to a smooth output, ranging from -1 to 1. This mapping resembles the way normalization compresses the inputs into a reasonable range. To enable more flexible input-output mappings, we introduce learnable parameters that adjust the slope of the transformation. Just like in layer normalization, we also add learnable scaling and shifting parameters gamma and beta. We call this the dynamic hyperbolic tangent, or DyT. This provides a drop-in replacement of normalization layers. The researchers trained both Vision Transformer (VIT) and ConvNext models on ImageNet 1K, covering both attention and convolution-based architectures. The training curves show similar patterns when using LN or DyT, indicating comparable learning dynamics. On ImageNet 1K supervised classification, DyT matches or outperforms LayerNorm across both architectures and model sizes. Similarly, for self-supervised learning on ImageNet 1K, DyT matches LayerNorm's accuracy across different pre-training approaches and model sizes. The trend holds for generative tasks as well. When evaluating image generation quality, measured by FID, where lower is better, on ImageNet, DyT achieves scores comparable to those of layer normalization across several diffusion transformer model sizes. When examining language model pre-training, the loss curves for DyT and RMS-norm models remain closely matched across different model sizes. As DyT involves only element-wise computation, it can achieve substantial reductions in both inference and training time. Here is the results of running 100 forward passes for inference and 100 forward-backward passes for training. But in practice, when modern compilers optimize LayerNorm, they are nearly as fast. That said, DyT is conceptually and computationally simpler and eliminates the need for reduction operations. As a result, it can be faster in scenarios where reductions are expensive and is also easier to fuse with surrounding layers for potential speedups. But how does DyT actually stabilize training as normalization does? Let's visualize this in 2D using root mean square normalization. Here, the normalization effectively maps all the points onto a unit circle centered at the origin. This mapping requires us to compute the lengths of the 2D vectors. In contrast, here is how the hyperbolic tangent function handles the same points. Despite being element-wise only, tanh also bounds the points just within a square instead of a circle. Implementing DyT is straightforward. This layer receives an input tensor X with shape batch size B, sequence length T, and embedding dimension C. During initialization, we specify the learnable parameters, including alpha, which controls the slope of the tanh function, gamma for scaling, and beta for shifting. The forward pass of the layer applies the dynamic tanh transformation to its input, combining the learnable slope, alpha, scaling, gamma, and shifting beta parameters to produce the output. All of these operations are highly parallelizable and performed element-wise. The tanh function works pretty well, but can we do better? By analyzing the fundamental properties that make point-wise functions effective for model training, the authors systematically explore a wide range of possible designs to identify the most suitable function. After trying many options, researchers found that the ERF function performs the best. The error function ERF of x gives the probability that a Gaussian random variable with mean 0 and variance 1/2 lies between -x and x. We add a learnable slope parameter alpha, just like with DyT. In addition, the authors find that adding a learnable bias parameter S can make this layer even more expressive. This becomes the dynamic arrow function layer, or Derf. Both alpha and S are learned during training, optimized alongside all other weights. Now we can measure the performance of these layers on diverse problems. We have ImageNet 1K classification accuracy on the left and image generation quality on the right. The previous hyperbolic tangent layer can match the performance of layer normalization. Surprisingly, the new dynamic ERF layer surpasses both alternatives. The same trend holds for other problem settings, including speech models and the long-range DNA sequence modeling task. This challenges the widespread assumption that normalization layers are essential components of deep learning model training. The authors further demonstrate that incorporating a learnable bias term S into the element-wise function consistently improves performance, regardless of the specific function used. In summary, it's remarkable that simple element-wise functions can not only match, but sometimes even surpass traditional normalization methods. It highlights how much remains unknown about deep learning. Thanks for watching, and I'll see you next time.